Let's go back to our example. So before, during our previous lecture, we derived this equation. So we derived the equation, only then we were able to create a graphical representation via block diagram. For the bone graph, we start with the graphical representation that we conducted. So for the C element, the integral causality will be when we feeding it with the flow, and the effort goes back at the feedback. For the R element, the same. We need to send the flow, because it will be the same. One element, the flow is the same, and it's pretty convenient. We already know the velocity, we can send it for all the system. But for I element, we need to send an effort. Yeah. So you can see that the strokes, causality strokes, are the same like in the picture. So E1, the effort for the source of effort is the something that we set up, and since we know it, it will be minus mj. Okay? Do you agree that the effort E1 equals to minus mj for our system?
Why minus? Why not?
Because we chose the direction of y going up, and the body, when the spring is deflected, generate force to go down.
Yes, because the flow starts from the left to the right, so it's separated after the...
It's like it is the axis, initial position of the body. This one, we deflected the spring on the distance x.
For example, that,
And the motion of a body looks like this. So it's want to go down. This is minus. Direction of the motion. If we chose the direction of motion like this, it will be positive. But the initial position will be minus 1, not 1. All right, for the one junction, is it clear now that all the flows will be the same? It will be equal to the x dot, the velocity. And since it's one junction, we need this equation. And we already know E1. For the C element, we can calculate E2 because we have an integral causality when we feed it with the flow. So 1 over C equal to the coefficient of stiffness. Integral of flow equal to the x dot. So integral of x dot equal to the x. So E1 it's minus mj, E2 is a kx. E2 this is E2. E3 it is a damping, and we know that it's damping coefficient times velocity. And for the I element, we need to feed it with the force. But we do not know force. But we actually can calculate it out of this equation. We can derive it E4. And E4 will be equal to the E1 minus E2 minus E3. And we will be left with the minus mj minus kx minus bx equal to the force which is applied to the body, where the force F, due to the second Newton's law, actually mx double dot, and we can check it. We can put this kind of force into the equation, and we'll get that flow actually equals to the velocity. Everything is correct. So we derived an equation just to check, but we actually do not need it. We created the simulation model just out of inspection. We take a look at the picture, we saw the elements, we consider the causality. This is our model. And there is a simulation package like a 20 sim that allows to model this bond graph. And we can run it and we will see the results of simulation. And if we go inside, we will see the equation for the flow. PE is efforts. But PE, it's something we send it as the input to the E element. As an output, we calculate flow. So effort goes in. Flow is like a feedback, and this is why we have an equation for the flow. If we go to the C element, we will have an equation for the effort right here. So it will be state divided by C. What will be the effort for the spring? It will be force, right? Right? State, it is integration. You can see here. It is integration of flow. Flow is a velocity. If you integrate velocity, you will get position. It is state. Divided by C, C is the compliance. It's the opposite of coefficient of stiffness. So here, what we can see, it's like deflection times coefficient of stiffness. And actually, it's pretty much the same equation. Where is MATLAB? That you will see here. But here F is the force, not flow. Force equal to the damping coefficient times velocity. This thing. D, coefficient of stiffness, V, velocity. Coefficient of stiffness times velocity. Spring. Force equal to the coefficient of stiffness times state. X is the state. Pretty much the same equation. So the way how we do it in simulation, we take the icons, the blocks, and we create an assembly of these blocks in order to do the simulation model of our system, and the equation will be derived automatically due to this same rules of bond graphs. Here you can see another examples. So we considered only when the spring and the damper in parallel, but also you can do this in series. In this case, you need to use a zero junction. You can think it by your own as a practice. Here is the same, but for electrical system in parallel and in a series. Okay, but still those are pretty simple. But actually you can do multi-body dynamics using these bond graphs. For example, here you can see Chebyshev linkage mechanism, and this is done in 20 sim. So you can do multi-body dynamics. But now I will show you the bond graph for this linkage. Are you ready? Actually, I need like maybe 1-2 minutes to explain you, and it will be very easy. Look. It looks scary, I know. And it took a while for me to create this model. Let's assume we have a body with the joint A and joint B and gravity of center here. It's a body. What kind of element do we use to model a body? Inertia. What kind of element? I. All right. I. And inside I, we put an inertia for the body. We can do it, already for the x and for the y. If we use then one junction, here will be, what will be? Here will be the velocity of center of gravity. Do you agree? Of center of gravity, of point J. So here will be the velocity of J, x. And here will be, yeah, sure. Causality, yeah. Yes. Velocity G, Y. All right. What will be the velocity of point A? Velocity of point A equal to the velocity of point J plus an relative velocity of point A around J. It will take the same true for the B. And if we derive an equation for the x and y, we'll be left with the sentence here will be Jx, and here will be sinus theta times this lever. So actually it will be those equations. Okay? MTF, it's transformer, but modulated transformer. So transformer, just transformer, when your coefficient k, for example, is constant, modulated when it is a function. So let's assume that here we have a motor and angular velocity. It means the angular velocity will be the same for all body. So here is 1 for the angular velocity. Modulated transformer. The coefficient there will be this distance times sinus theta, according to the equations. Okay? How can we calculate theta? We do integration of angular velocity. So here you can see a sign of integration. It is used to calculate theta, and it's go as an input into modulated transformer. It depends on theta. All right. So now we do understand those blocks. So this is known, right? Also, we do understand these elements. It's I with the causality strokes. What is the zero? Zero is the junction when we need to sum velocities. We sum absolute velocity plus relative velocity. And in the end, you will get the velocity of A for the x and for the y component. So it will be Ax, it will be Ay, Vbx, Vby. That's it.
As an input to the zero, we have Vg plus the relative velocity, which is the rotational velocity times sine theta or something. But on the one above, what's the input from theta? How theta is an input to the
Input of what?
theta 1 out.
Theta 1 out? You mean this?
No, vertically, the one above, yes, down a little bit. Yes, here. How is this an input from behind, from the bottom to the one? The arc.
Input of velocity?
Theta is input of this node.
Theta is an input of this.
Theta. You mean this thing?
Yes.
Theta out. it do not go into the one junction. It's just the way of representation. You can see that here on the bottom, y it do not depends on the theta. It just
It's just for the text.
yeah. One velocity of j, x and y do not depend on theta. Okay, so this is the way how we do modeling of a rigid body. As for the joints, you see we use this structure. It's like we put in a joint a spring and a damper. It's like we have a body with a very stiff spring for the x component. Let me rewrite it. Very stiff spring for the x component and for the y component. It prevents from the motion along xy, but it allows us to do the rotation motion. Okay? 0, it means that we need to sum here reaction forces. So, and basically that's it for the mechanism, but still it's not very convenient, and because it's one-dimensional bond graph. Actually, in practice, we use multi-dimensional bond graphs where each bond is not a scalar value but a vector. And in this case, you will do correctly, the bond graph will look like this, very nice and shiny. Explanation of these terms I will give you during the next lectures, but basically P is the momenta, P dot is the force. If you multiply these components with the velocity, T is a twist, it's a spatial velocity, you will have the equation for the body. 3, it is the force which goes inside the body. For example, when I play with the body, so now I'm sending power to a body, which is denoted by the 3. 1 is the energy which is stored in the body, and 2 is something which is called gyroscopic effect. And here you can see it's clearly that it changed the orientation. And we can see this effect in the equation. All right, we do not have time for the DC motor, but you can do this as a practice. For example,